Hi everyone, I'm Destiny Clowers,
I'm Andrew Brown.
and today we're going to be going over Module 4 questions. So I've got a question for Andrew right off the bat. Andrew, what type of rigid motion is this?
Well, this rigid motion is actually called a translation, otherwise known as a slide, because the figure literally just slides over. A translation takes place when all the points on the plane are moved the same distance in the same direction. An arrow also has to be drawn from one of the original points to the end of the translated points in order to find a translation. This is called a slide arrow, and this arrow defines two things. The direction of the slide is the direction of the arrow, and the distance moved is the length of the arrow. Thanks for asking, Des.
You're welcome.
Now, I have a question for you. What would this figure look like if it were reflected over this line of reflection?
Well, first let's look at what a reflection is. So a reflection, or otherwise known as a flip, is one of the four rigid motions in which all points from the first figure are transformed to the opposite side. All of the points are the same distance away from a determined line, with the same distance away from the line. So if we look at this point right here, it's going to be the same distance away from the line on the opposite side. And same with these points, even the one up top. And you just keep repeating that motion with all of the rest of the points, and eventually the figure will look like this. So this is what it would look like when it's reflected over this line of reflection.
All
Thank
right.
you.
Yeah, thank you.
Okay, Andrew, can you explain why these figures have rotational symmetry?
Yeah, of course. It's a great question. Well, a figure has rotational symmetry if it can be rotated 180 degrees around its center and end up in the exact same location that it was before it was ever rotated. So all the lines should match up perfectly after the rotation. So, for example, this diamond right here to the left, when it's rotated 100 degrees, it looks exactly like it did before the rotation. Same with this triangle in the middle. After the rotation, all the lines match up perfectly, as if it was never rotated. And lastly, the one on the right is a hexagon. This also matches up perfectly even after the rotation. This is how you know that each of these figures have rotational symmetry. And I have a question for you. Can you explain why these figures don't have rotational symmetry?
Sure. So, like you just mentioned, rotational symmetry is when a figure can rotate 180 degrees around its center and look exactly like it did before it was ever rotated. Each line should match up perfectly, just like you were saying. So, we'll take a look at this triangle. And when it's rotated 180 degrees, the lines don't match up perfectly. It's not a perfect image like the first one. So that's how you know this one doesn't have rotational symmetry.
Okay.
Now, this shape is called a chord, and once it's rotated 180 degrees, it looks like this. So once again, the lines don't match up perfectly, and the second image doesn't look like the first.
Right.
And same with this last triangle. When it's rotated 180 degrees, it ends up looking like this. And since the lines don't match up perfectly, since the two images don't look exactly the same, that's how we know that these figures don't have rotational symmetry.
Okay. All right. Yeah, thank you.
Of course. So Andrew, how many lines of symmetry does this hexagon have?
Yes, that is also another great question. So let's look at what a line of symmetry is. First off, a line of symmetry is the imaginary line where you can fold the image and have both halves match exactly. It's a perfect rotation. So let's see how many this hexagon has. So here's one, and here's another one, and another one, and one more after this. Bam. So that means there are 6 lines of symmetry.
Good job. Thank you.
So I have a question. Another one. What is tiling? Can you give me an example?
Sure. So we learned in our textbook that tiling is when you cover a figure or the whole plane with tiles. When you do this though, there can't be any overlapping of the tiles and there can't be any gaps between the tiles. So here's an example. This is the first hexagon that we have, and then I created these next few hexagons, and you can tell that there's not any overlapping, there's not any gaps, and when we add the next layer, it looks like this, and there's still not any overlapping and there's not any gaps. So this is an example of tiling, and you could honestly continue the process and keep adding more hexagons all the way around here, and there still wouldn't be any gaps or any overlapping.
All right. Yeah, thanks.
You're welcome. So why is angle QVP a right angle?
Okay, yeah. The reason why angle QVP is a right angle is because the two lines actually meet at the very center. You can see this little red rectangle at the very top left corner of where these two lines intersect. That just indicates that it's a 90-degree angle. So with these two lines that meet at the center, they just create perpendicular lines that do form that 90-degree angle. So that's why angle QVP is a right angle.
Awesome, thank you.
Yeah. So how can you prove that angle QPT is congruent to angle SPT?
All right, so to prove that triangle QPT is congruent to triangle SPT, we're going to begin by looking at a reflection. So as you can see, this line right here, it's met by both of the triangles. So if this triangle was reflected over this line right here, it would look exactly like triangle SPT. So since these two triangles are a perfect reflection of each other, this is how you know that these two triangles are congruent to one another. So that's how you would prove that, is through this reflection image right here.
All right.
Okay, Andrew, so in this image right here, what does the number 5 represent?
Well, the number 5 in this problem actually represents the number of angles within the pentagon. Since
Okay.
5 sides make up every pentagon, we know that there will be 5 central angles, right?
Right.
So just within the triangle. So we also know that the central angles of a pentagon measure up to equal 360 degrees. So to find out the measure of the individual central angles, we will divide 360 degrees by 5. This just means that each individual central angle within the pentagon will equal 72 degrees. This is a crucial step to figuring out the rest of the problem.
Awesome. Okay.
So how do we know that angle NOQ is 24 degrees?
So this is kind of a addition to your last problem because we have to look at the central angles for the pentagon and the triangle in order to find out that NOQ actually is 24 degrees. So like you were just saying in the previous problem, the pentagon central angles equal 72 degrees because, like you mentioned, there's 5 central angles, and since they all add up to 360 degrees, we divide them by 5, and that equals 72 degrees. Now the next step is doing the same thing for the triangle. So there's 3 central angles within a triangle, and because those angles all add up to 360 degrees, we're going to divide that by 3, and that gives us 120 degrees. Now all we have to do is subtract 122 degrees from, or 120 degrees from 72 degrees, and that gives us 48 degrees. Now we have to divide 48 by 2, because if you look at this image, O is the radius, and the angle NOQ, it's met in the radius of the the center of this circle, which is the radius. So that means we're going to have to divide it by 2 since we're not looking for the whole diameter of the circle. So once we do that, we get 24 degrees. So that's how we know that angle NOQ is 24 degrees.
All right, cool.
Okay, Andrew, I have another question for you.
Okay.
What is an equilateral triangle? Can you find the measures of each interior angle?
Why, certainly. An equilateral triangle is actually a triangle with the same side lengths and the same angle measures. Probably one of the easiest triangles we can distinguish of all of the triangles we can think of because everything's equal, hence equal and equilateral.
That
So
makes sense.
it's pretty easy. We can find the measures of those interior angles too, just as easy. So we know that the interior angles of a triangle must add up to 180 degrees, right?
Right.
So since there are 3 interior angles, all you have to do is just divide the 180 degrees by 3, and you just get that 60 degrees for each of those angles.
Okay.
Yeah,
Well, perfect.
yeah. And I believe this is our last question.
Yes.
How tall is the cliff?
Well, that's a good question. Here's the picture that goes along with your question. And you can see that there is one triangle located right here, and there's another triangle right here. So in order to figure out how tall the cliff is, we have to begin with what we know. So here's what we know from the problem that was given to us on last week's homework. The ruler is 2 feet in front of Jenny's eyes. So that's kind of what this triangle right here represents. She's holding the ruler right here, and it's 2 feet in front of her eyes. So the next thing we know is the top and the bottom points of the cliff are only 1.5 inches between ruler markings. So when she's looking at this cliff right here through her ruler, it's only 1.5 inches tall. Now, Jenny is also a quarter mile away from the cliff, and it tells us that 1 mile equals 5,280 feet. So to solve for the height of the cliff, we're given this equation. And this equation states that the distance between ruler markings divided by the distance from eyes to ruler equals the height of the cliff divided by the distance from the cliff. Now we're going to just plug in everything that we were given in the problem. And once we do that, we get 1.5 inches divided by 2 feet equals the height of the cliff divided by a quarter mile. Now, to finish this problem, it's going to be a lot easier if each of the units are the same. So we're going to change inches and a quarter mile to feet so that we can better calculate this.
Okay.
So we're going to times 1.5 inches times, 1.5 inches times 12 inches. When we do that, we get 0.125 feet. And for the quarter mile, we know that we're going to have to divide this 1 mile by 4 because 4 quarters make up 1 mile. So when we do that, divide this number by 4, we get 1,320 feet. So now, as you can see, all of our units are in feet, so it's going to be a lot simpler to solve. So now we're going to multiply this side by 1,320 feet. That means that that number crosses out. And then we're going to multiply 1,320 feet by 0.125 feet divided by 2 feet.
Okay.
And once we do that calculation, we get 82.5 feet.
Oh,
That
okay.
means that the cliff is 82.5 feet tall.
Wow.
So I
Okay.
hope that answered your last question.
Yeah, yeah, it did. Thank you so much for showing me some insight on those things.
Of
Yeah,
course.
yeah.
So that's the end of our Module 4 presentation. So if anyone else has any other questions, just feel free to ask us, and we would love to answer this for you guys.
Yes, please.
Well, we hope that y'all have a good night, and we are going to sign off of here now.
Thank you.
Yes, thank you guys. Bye-bye.